This is a production of the Chemical Education Material Study.
When sugar dissolves in iced tea, the tea becomes sweeter. But after a certain point, no more sugar dissolves. Then the sweetness of the tea stops changing. We have reached solubility equilibrium. When ice is added to tea water, ice melts and the tea gets colder. When more ice is added, the temperature reaches 0 Celsius and becomes constant. Adding more ice does not affect the temperature. We have reached temperature equilibrium. Another solubility experiment, solid iodine dissolving in a mixture of ethanol and water. The color change shows that iodine molecules are leaving the crystal to become part of the liquid, forming a solution. As more iodine dissolves, the color intensifies. But after a few minutes, the color stops changing, though solid iodine remains. Apparently, the concentration is now constant. Again, we have reached solubility equilibrium. Equilibrium is the subject of this film. To investigate equilibrium, we will consider two questions. The first question is, how do we recognize equilibrium? This question is answered by observation of macroscopic properties. Observations performed on visible amounts. The second question is, how do we explain equilibrium? This question is answered in terms of molecular behavior. We recognize equilibrium by observations on large amounts of substance. We explain equilibrium in terms of the behavior and properties of individual molecules that we cannot see. Equilibrium is best explored by observing a system containing a fixed amount of material with nothing being added or removed. For instance, consider these two fish bowls. Watch the concentration of fish in each bowl. At first, all of the fish are in one side. When the barrier in the middle is removed, the fish can move to the other side. Now, some of the fish, swimming around in their random way, begin crossing into the second bowl. As they do, the concentration of fish in the first bowl decreases and the concentration in the second bowl increases. Even had the bowls differed in size, the concentration, that is, the number of fish per liter of water, would have become the same throughout the system. Equilibrium now exists. Now let's look at these two glass bulbs. The right-hand bulb contains the colored gas bromine. The mercury levels in the manometer show that the bromine pressure in the right bulb is about 100 torr. The oil in the manometer is there to prevent reaction between the bromine and the mercury in the manometer. This second bulb has been emptied with a vacuum pump. The mercury levels in the left manometer show the pressure is 0. At first, all of the bromine is in one of the bulbs. Now let's open this stopcock so the bromine has access to the other bulb. There it goes. As the color appears in the left bulb, the pressure rises on the left manometer, while the other manometer shows that the pressure is dropping on the right. Everything settles down quickly. The colors are no longer changing, and the pressures in the two bulbs are now equal. We have reached pressure equilibrium. We recognize it by two constant macroscopic properties, the pressure and the gas color. The presence of chemical equilibrium is recognized by constant macroscopic properties when nothing is being added to or taken from the system. Sweetness becomes constant. Temperature becomes constant. Concentrations become constant. Color intensities become constant. Gas pressures become constant. Now let's turn to our second question. How do we explain equilibrium? To understand this behavior, we would like to see what individual molecules are doing. Perhaps our goldfish bowls will show us how to find out. In our goldfish bowls, we can see that each individual fish is moving about. It is hard to follow the path of any one of them, though. They all look the same. We need a way to mark a few of the fish so we can distinguish them. Here are some dark fish. Suppose we add a few of these to one of the bowls. The small number of fish we add does not disturb the concentration noticeably, but now we can follow the movements of these marked fish. See where this one goes. This particular fish is moving from the right bulb to the left bulb, even though we have equal concentrations of fish in the two bulbs. Some fish are going in the other direction, though. In this system, you can see that concentration equilibrium is a dynamic process, a balance between gain and loss of concentration. Unfortunately, we can't see individual molecules, but we can track radioactive molecules, even at such low concentrations that there is no health hazard. This bulb contains an aqueous solution of radioactive bromine. When one of the radioactive bromine nuclei disintegrates, a gamma ray is emitted that reveals the approximate location of one of the bromine molecules. By detecting such gamma rays, we can follow the movements of these radioactive molecules just the way we watched the dark fish move about. On top of these recorders, we have a gas setup like the first one, except with this small bulb containing some radioactive bromine gas attached here at the side. The amount of radioactivity in this sample is so low that we don't need any protective shielding. Let's look over the experimental setup. The manometers show that the pressures in the two bulbs are equal. Pressure equilibrium exists. Beside each bulb, there is a radiation detector, a Geiger counter. When this detector is near a source of radioactivity, the number of atoms disintegrating per second is shown on a counter meter. At the same time, a recorder makes a graph of it on a slowly moving chart. The recording pen is right underneath the indicator arrow. Now we have a way to follow movements due to individual bromine molecules. Let's allow a very small amount of radioactive bromine to enter the large bulb. Watch the indicator on this right-hand recorder. It shows that radioactive bromine has entered the right bulb. Meanwhile, the left recorder shows only background radiation. Gas color is constant in both bulbs, and the manometers show no change, so we still have pressure equilibrium. Here's the chart again after 2 hours. The indicators have moved a little bit, though the pressure continues unchanged. Let's wait another 2 hours. Now there has been a substantial increase in the radioactivity in the left bulb. Though the pressure isn't changing, the radioactive bromine continues to move into the left bulb. Here it is after 2 more hours. Apparently, those gas molecules containing radioactive bromine nuclei are moving from the right bulb to the left. Since pressure is constant, molecules must be moving in the other direction also. It is clear that molecules move back and forth, even though color and pressure remain constant. We see that pressure equilibrium is explained in terms of dynamic molecular behavior, just like the fishbowl equilibrium. But what about solubility equilibrium? Is it the same? Let's add some solid iodine to our original saturated iodine solution. The color doesn't change. Now let's add some radioactive iodine. Radioactive iodine is like ordinary iodine, except that now and then one of the iodine nuclei disintegrates and changes into another kind of nucleus. We can spare a few, since we have about 10 to the 23rd of them present in the sample. Look at the radioactive iodine. It looks identical to ordinary iodine, the same lustrous gray plates. We add some to the saturated solution. Equilibrium is already established, of course, so the concentration doesn't change. But what about the radioactivity? Has any of the radioactive iodine gone into solution? To find out, we pour off some of the solution, leaving all of the solid behind. Now we can test for radioactivity in the solution. The small deflection on the meter shows a low level of radioactivity. Some of the radioactive solid has dissolved. Here is the same measurement an hour later. Now the meter shows that much more radioactive iodine is in the solution. The radioactive solid continues to dissolve. Yet, while all this was happening, the color of the solution didn't change. An exactly equal amount of iodine must have returned to the crystal. Let's go back and take a closer look at the entire process. When a crystal of iodine is dropped into the liquid, solid begins dissolving immediately. We would like to watch this occur on the molecular level, but we can't see individual molecules. The best we can do is to consider molecular models which show what chemists believe is going on. We picture the iodine crystal as an array of iodine molecules placed in the regular positions of a molecular crystal. Around the model of the crystal, we place models of water molecules, mixed with models of the larger ethanol molecules. These molecules are in random orientations to represent the liquid state. To be realistic, all of the molecules should be in motion. Now, to focus our attention on the iodine molecules, we'll ignore the water alcohol solution. All of these molecules in the crystal should be in motion too, but it is difficult to show movement in the entire lattice, so we'll be content to show how vibrational energy of individual molecules permits them to escape from the crystal. At first, there is only one process. Iodine molecules leave the crystal and become part of the liquid. As the concentration of dissolved iodine rises, some molecules find their way back to the crystal. But at first, the rate of dissolving is higher than the rate of crystallization. The rate at which molecules leave the crystal is constant, as fixed by the surface area and temperature. The rate at which molecules return to the crystal depends on concentration as well. As the concentration of dissolved iodine rises, the rate of crystallization rises. In time, the concentration rises enough to make the rate of crystallization equal to the rate of dissolving. Then molecules return to the crystal at exactly the rate at which they have been leaving. The concentration becomes constant. Dynamic equilibrium has been reached. The two opposing reactions, iodine dissolving and crystallizing, are now proceeding at equal rates. There is one more experiment we can try with this iodine solution. Though we didn't show it with our models, a bit of the dissolved iodine reacts with water, forming iodide ion, I-, and iodate ion, IO3-. 3 iodine molecules plus 3 waters react to give 5 iodide ions, 1 iodate ion, and 6 hydrogen ions. Iodide ions can be detected by adding a solution of lead nitrate. Since lead iodide has low solubility, the presence of I- would be shown if a precipitate appears. The solid is lead iodide formed in the reaction lead ion plus 2 iodide ions gives solid lead iodide. Now, our radioactive iodine will show whether this chemical equilibrium is also dynamic. If any radioactive I2 molecules have changed into radioactive iodide ions, then some radioactive iodides must be present in the solid lead iodide. The precipitate should be radioactive. Let's see if it is. Before we can check the precipitate for radioactivity, it must be freed from the liquid, which we know contains radioactive I2 molecules. When the filtration is complete, the precipitate is washed to remove the last trace of the radioactive iodine solution. Now the dry yellow precipitate of lead iodide can be tested for radioactivity. Yes, there is radioactivity in the solid lead iodide. We added solid radioactive iodine to the saturated solution. Though solubility equilibrium existed, radioactivity was soon found in the solution. The dissolved iodine reacts with water. Because this chemical reaction is also a dynamic equilibrium, radioactivity appears among the iodide ions and iodate ions. Thus, when lead nitrate is added, some of the solid lead iodide formed is also radioactive. Iodine molecules are continually reacting to produce iodide, iodate, and hydrogen ions. But the reverse reaction occurs at the same time. Equilibrium exists when these two opposing rates become exactly equal. Here we find that chemical equilibrium can be explained by picturing dynamic molecular behavior involving balanced opposing reactions. Now we have answered our 2 questions about equilibrium. We recognize it by constant macroscopic properties. We explain it in terms of the dynamic behavior of individual molecules. Equilibrium represents a state of balance between opposing reactions. This understanding of equilibrium aids us in predicting and in controlling chemical reactions.